Okay, so now we will learn how to compute the sample size for design experiments. Design experiments are the ones that use Anova at the core. So we will have one-way Anova, two-way Anova, two-way Anova with interactions, or three-way Anova, and so on. We will distinguish two different kind of sample size calculations. The first one is this group, which is the more standard Anova analysis with fixed effects, while this second group will consider random effects, and we will separate them in two videos. So let's start with the one-way Anova with fixed effects. This is also called a completely randomized design. Okay, so let's say that we are testing 4 different drugs for hypertension, and we wonder if there is any difference between the 4 drugs. And yeah, so we will be a bit more precise later when we calculate the sample size. So this is a one-way Anova. So we have 4 different drugs, and the Anova null hypothesis is that all the means are equal, so that there is no difference between the different treatments. And the alternative is that there are at least two treatments whose mean is different. Unfortunately, this web page doesn't exist anymore, so we cannot check it. But the idea is that if there are differences in at least 2 groups, so for instance this group is different from this other. Okay, then each one of the treatments will have a sample size Ni, and the total sample size will be the sum of each one of the groups. And here is a little bit of reasoning of how we will analyze the data. So first we will compute the overall mean. So that is summing all our observations and dividing by n. Then we will compute the mean of each one of the cells. So we take the observations of a cell and divide by the number of observations in that cell. And then the effect caused by that treatment will be the difference between these two. There are many small subtleties here, but this equation is true for perfectly balanced designs. But let's keep these things simple. So and then we will estimate the within cell variance, so how variable data is in each one of the cells, and we will assume that all cells are equally variable, so that we can use all information from all cells to compute their variance of the residuals. Okay, so the Anova model is this one. So a given observation is something that depends on an overall mean plus something that depends on the effect of the treatment you have received, the treatment I, plus something that depends on that particular person. And then we will have this sum of squares, and this total sum of squares, and this sum of squares of the errors. And for each one of these sums, we will have an associated number of degrees of freedom, that we can think of them of how many parameters you have used to express all this sum of squares. So for instance, here if we have I treatments, we will have I minus 1 degrees of freedom for the treatment, and then n minus 1 degrees of freedom in total, and then the error will be the difference between n minus 1 and I minus 1, that is n minus I. So we will divide the sum of squares with by the number of degrees of freedom. So we will have the sum of squares of the treatments divided by the degrees of freedom of the treatments, and for the error we will have the sum of squares of the residuals divided by the degrees of freedom of the residuals. And then we will compare these two. These two are called the mean squares. So the F is the ratio between the mean squares of the treatments divided by the mean squares of the residuals. So if there is no difference, between treatments, then that is the null hypothesis, then this f of the treatments will be distributed with a central Snedeker f with df degrees of freedom for the treatment with this number of degrees of freedom for the residuals. And if there is a difference, then this f will be distributed differently, so it will have the same number of degrees of freedom, but it will have a non-centrality parameter that is given by this one. Okay, so as always, so we have two opposing distributions for the f. So one that is when the null hypothesis is true, another one that is when the alternative is true. We will have to find a critical value that beyond that point we will have alpha on the null hypothesis and beta from that point to the left on the alternative hypothesis. And so we have to find an n such that, and a critical value such that this area to the left is alpha, this area to the right, to the right is alpha, to the left is beta. So this is somehow encoded here. Okay, so let's give an example. So let's say that we have a balanced ANOVA, so all the cells have the same number of observations, and if it is not, we don't have the same number of observations for all cells, we have an imbalanced ANOVA. And there are two important cases of interest. So one is the two treatments that are biased symmetrically. So let's say that all the alphas are 0 except two that is different, that are different. The other one is when one of them is on, or only one of them is different, and then this is the distribution of weights that we have. Okay, so all of them are equal except one that is of this size. Why these specific values? Because the sum of all the alphas have to be 0. So the sum of these two have to be 0, and sum of all these have to be 0 too. Okay, so let's say that we want to design to detect a change of 10 in one of the groups. So we are measuring values, and the values, the overall mean is 50, and we want to be able to detect a change of 10 in one of the groups. And let us assume that the within cell standard deviation is expected to be 8. Okay, so let's see, what is the overall mean? The overall mean is this one, so it is 47.5, because we will have in one of the groups 40, in the other three groups we will have 50, and then we have to divide by 4 times the number of observations in each one of the groups, so it is 47.5. So these 40 give us a change of minus 7.5, while the other 3 will be an extra 2.5. So now we have the configuration of changes. So now we can compute the non-centrality parameter. Let us go to here. So the non-centrality parameter is the sum of squares of the treatments divided by the variance of the residuals. Okay, so what is the sum of squares of the treatments? So we will have n0 individuals in the first group, but the first group has this alpha, so it will be n0 alpha squared, and then the same for the other groups, and divided by sigma squared. So here we have 1.17 and 0. And what we need to solve is the following equation. So we need to solve, this is f 1 minus alpha, and then the number of degrees of freedom of the treatments, but because we have 4 treatments, we will have 3 degrees of freedom for the treatment, and then this is total n minus I, so it is 4 and 0 minus 4, and then on the other side we have the beta, so we have f beta, and then the non-centrality parameter and then the same number of degrees of freedom. So we solve for this equation and we have n naught is equal 13.13. So that means that we need 14 samples per treatment. Very good. Okay, so let's complicate this a bit more, and now let us introduce blocks. So let's say that we assume that we are measuring blood pressure, and there are differences between males and females in blood pressure. So now our model will be an observation will be an overall mean plus something that depends on the treatment plus something that depends on the block, that is the male or female, plus something that depends on the person. And when we are comparing our treatments, we are comparing the sum of squares, or the mean square of the treatment to the mean square of the residuals. So all the variance explained by the block will be taken out. Okay, so let us make this separation of how to estimate the different contributions of the different alphas and betas. So we would have the overall mean, the mean of all people, male or female, that have received the treatment I, and then we would have the mean of all males and the mean of all females, and then we would have the mean of the groups. So that would be a treatment. So let's say that we have a control and then 3 drugs, and then we would have the control male, so the mean of the control male, control female, drug 1 male, drug 1 female, and so on. And then we can compute the contributions of each one of these alphas and betas, and remind these equations are true only for the balanced cases. Okay, so we will have our Anova table. So we have in total n minus I degrees of freedom, and this n minus I we are using I minus 1 for the treatments, j minus 1 for the blocks, and all the remaining, that is n minus 1 minus these 2, for the residuals. And when we compare our treatments to say whether the treatments are significant or not, we compare these mean squares to the mean squares of the errors. So it is this f that we are looking at. So the number of degrees of freedom will be I minus 1 and then these ones. And there is a change with respect to the previous case, because the number of degrees of freedom of the errors has changed from here, n minus I, to this one, Okay, the number of degrees of freedom of the treatments has not changed. And the non-centrality parameter, it is again the same one as we had before. And again, to find the number of elements in each one of the cells, we need to solve for this equation. We need to we have to find an f such that from that f to the left we have from this f to the left we have beta, from this f to the right we have alpha. Okay, so given the example before, we would have exactly the same data. The non-centrality parameter is calculated in exactly the same way, and the equation is almost the same, only that the number of degrees of freedom for the noise has changed. So before we had 4 n0 minus 4, now we have minus 5, but still n0 is almost the same. So an important message here is that checking for differences in blocks is very, very cheap, because we will use very few parameters to describe those differences. So before we had 13.13, now it is 13.14, which is almost the same. Anyway, we will use 14 people per group, but now we can have within the groups, we will have 7 males, 7 females, and we have still the same power as before, or almost the same power as before. And so considering blocks is a very good idea, and because you can generalize much better your results, and it doesn't cost that much in terms of sample size. Okay, so let's go with the next one, that is the full factorial design with fixed effects. Okay, so let's say that we have three factors. So we have two doses, dose 1 and dose 2, three dosing regimes. So we have three different regimes. That will be factor B, and then we have 5 different drugs. And we presume that the standard deviation of the blood pressure is 12, and we want to detect changes of at least 20 between any two drugs, and we want to detect that with a statistical power of 90%. How many individuals do we need for each one of these combinations? Okay, so let's see. This, by the way, we also want to model interactions between drugs and dosing regimes. Okay, good. Okay, so our model will be this one. So it will be something that, so our measurements will be something that depends on an overall mean, plus something that depends on A was the dose, plus something that depends on B was the dosing regimes, and something that depends on the drugs, plus the interactions between regimes and drugs. And let's design for the main effects. So we want to detect a change of 20 between any two drugs. So that means that this is the kind of changes that we are looking for. So minus 10, 10, or minus 10, 10, 0, because this doesn't change, or minus 10, 10, and then 0, 0, 0. Okay, and we already know how to count the number of degrees of freedom. So we have two doses, so we will use 1 degree of freedom for the doses. We have three different kind of regimes, dosing regimes, so we will use 2 degrees of freedom for that. 5 drugs, so we have 4 degrees of freedom. The interactions between drugs and regimes, it is the multiplication of these two, so we will have 8. And in total, for each one, so if you count how many combinations do we have, so we have 2 times 3 times 5, that makes 30 groups. So we will have 30 times n0 measurements, and for the total we will have 30 n0 minus 1 degrees of freedom. So how many do we have for the errors? We have the difference between these 30 n0 minus 1 and the sum of all these. So the sum of all these at the end, it is 30 n0 minus 16. And when we are comparing our drugs, we will compare drugs versus error. When we compare the regimes, we will have regimes versus error, or doses versus error. Okay, so now we will compute the sample size for each one of the main effects. So what is the non-centrality parameter for A? So for A, we have to count how many groups do we have of each one of the A's. So the A was the doses. We had 2 doses, and we had 3 regimes and 5 drugs. So we have 3 times 5 groups. Each one of the group has a size n0, and the difference is caused by the doses. Let's say it is minus 10 and 10. That is what we want to detect. So this non-centrality parameter is this one. When we plug it into the equation, we see that we use 1 degree of freedom here, and the number of degrees of freedom for the noise, and then n0 is 0.7. So we need 1 person per combination. What about the dosing regimes? So the dosing regimes, we have 2 doses and 5 drugs. So for each dosing regime, we have this combination where they appear, and what we want to detect is this minus 10, 10, and this gives us a 13.89 and 0 for the non-centrality parameter. And then we have to solve this equation, but now it is 2 degrees of freedom and then the number of degrees of freedom. So this 2 is for the dosing regimes and these are for the noise. And then we have n naught equal 1.0 something. So that means that we will need at least 2 people per group to be able to detect these changes in the dosing regimes. And what about the drugs? So the calculations are the same, but now we will need 3 people per group. So to be able to detect these changes in any of the different factors, we will need to take the most restrictive case, that is this n naught equals 3. So we will need in total 90 samples because we have 30 groups and 3 individuals per group. Okay, so this would be all for the most simple cases, and then in the next video we will introduce random effects and how to compute the sample size for these random effects.